After having a preliminary discussion in the basics of solid state physics, we are now entering into a quite different topic, quantum mechanics. This is different in the sense that most of the concepts that we are going to discuss looks bizarre to most of us compared to classical physics. It is also inherently mathematical. However, the good thing is that these mathematical manipulations have absolutely nothing to do with the physical understanding of a situation. Most of us think in a classical fashion. We always try to get a perception of the concept in our mind about the things that we usually discuss. For example, when I say about a solid cube, you can quickly imagine in your mind how it looks like. Then, whatever properties that I discuss about the cube will be easily graspable. The unfortunate thing about quantum mechanics is that most of its concepts cannot be visualized. This difficulty, along with the unusual nature of quantum mechanical notations, make a first-time learner very difficult to grasp the subject. But as you come across many such things, ideas become more and more clear. Now, there must be an obvious question haunting your mind. Why do we need to study quantum mechanics if it is so strange and difficult? The answer to this question is very simple. This is the law of the nature. It describes how nature truly behaves. The physics before the advent of quantum mechanics, or what we popularly call as classical physics, including theory of relativity and electromagnetism, all are just a simplistic approximation of quantum mechanics. Typical engineering education in India does not provide enough space for quantum mechanics, and hence most of the things that we are going to discuss in next few modules will be new to you. This particular lecture is intended to provide you some preliminary information in quantum mechanics. We will have a systematic analysis of quantum mechanics from next class onwards. So before we start, just a word of caution. The famous scientist Niels Bohr once said that for those who are not shocked when they first come across quantum theory cannot possibly have understood it. Another famous quantum physicist, Richard Feynman, wrote about quantum mechanics as there was a time when the newspapers said that only 12 men understood the theory of relativity. I do not believe there ever was such a time. There might have been a time when only one man did because he was the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people understood the theory of relativity in some way or other, certainly more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. I have given these two statements here not to demotivate you, but to motivate you. If you feel it very difficult to understand the concept, then just keep in mind that this is quite normal. Even great scientists have had a tough time to digest quantum mechanics, so don't be panic. Feynman had also made a statement about quantum mechanics like this one. Do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you will get down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. So sometimes you have to accept the things that I tell you without worrying much how this happens so. In quantum mechanics, one of the crucial mathematical idea is that functions can be treated in a way that is fundamentally not that much different from vectors. A vector is usually shown in physics in the form of an arrow as shown here. Here f is a vector and fx and fy are its components along x and y direction. The same vector may be represented in another form as a spike diagram as shown in this bottom figure. This spike diagram is obtained by plotting the value of the components of the vector versus the component index. Since we are considering a two-dimensional vector here, it has only two components, fx and fy, which I have indexed as the index 1 and 2 respectively. In the same way as in 2 dimensions, a vector in 3 dimensions, or for example in 30 dimensions, can also be represented by a spike diagram. As the dimension increases, the index numbers become closely spaced, as you can see here in the second figure. For an infinite dimensions, the component index I can be rescaled into a continuous coordinate x, and the spikes are usually not shown in such plots, and the spike diagram becomes a function. So you can see that a function is just a vector in infinite dimensions. One of the important tools that we have to deal with vectors is dot product. It makes it possible to find the length of a vector by multiplying the vector by itself and taking the square root. It is also used to check if two vectors are orthogonal by checking whether their dot product is 0 or not. The usual dot product of two vectors f and g can be found by multiplying components with the same index together and summing that. I have used some numeric subscripts to specify the components of the vectors, and this allows the 3 times sum to be written more compactly like this form. The length of a vector f is indicated by putting two vertical lines on either sides of the vector, or by simply writing as f, and this is normally computed by this expression shown here. However, this does not work properly if we are dealing with complex vectors. The difficulty is that the terms of the form fi square are no longer necessarily positive numbers. For example, as you know, I square is -1. Therefore, we have to modify the dot product definition to include complex vector. We define the dot product for complex vectors like this expression in the second expression. Here, the vectors are written inside an angular bracket with a vertical line separating them. This notation is known as Dirac notation, and we will discuss more about Dirac notation in a later class. This means we have to multiply the complex conjugate of the vector written on the left side bracket with the vector written on the right side. Instead of dot product, we call this as the inner product for complex vectors. If the vector f is real, the complex conjugate does nothing and the inner product is same as the dot product. Otherwise, the inner product between the vectors are no longer interchangeable. The conjugates are only on the first vector f. Interchanging f and g changes the inner product's value into its complex conjugate. With this definition, you can see that the length of a non-zero vector is always a positive number. The inner product of functions is defined in exactly the same way as for vectors by multiplying the values at the same x position together and summing. But since there are infinitely many x values, instead of sum, we use an integral. The equivalent of the length of a vector in the case of a function is called its norm. Double bars are used to avoid confusion with the absolute value of the function to represent norm. A vector or function is called normalized if its length or norm is 1. Two vectors or two functions f and g are by definition orthogonal if their inner product is 0. Sets of vectors or functions that are all mutually orthogonal and normalized is called orthonormal vectors or orthonormal functions. For example, a set of functions or vectors f1, f2, f3, etc. is orthonormal if inner product of any of its components with any other component is 0 and with itself is 1. So the bottom line is that the inner product is just same as dot product but defined to handle complex vectors. According to quantum mechanics, the way that the old Newtonian physics describes nature is totally wrong if you examine it closely. For example, the Newtonian picture for a particle of mass m looks like this figure. In classical physics, it is possible to locate the exact position of an object, and it is also possible to measure its velocity with exact precision. Everything in classical physics is formulated based on this idea. But now we know that this is not true. So, what are the problems of this kind of a theory? According to quantum mechanics, there is nothing like exact location of an object. What we can say is the probability of finding the object somewhere at a given instant of time. Similarly, an exact velocity is also not there. When everything becomes probabilistic, how come it possible to predict the exact trajectory of an object? It is simply not possible. If it is wrong, then what is the exact theory? So that's what we are trying to understand in the coming classes. I just told you that in quantum mechanics there is nothing like an exact location for an object. Then how do we locate or study that system? According to quantum mechanics, what does exist is the so-called complex wave function psi of x, y, z and t. This is a function of time and position coordinates. The problem is that we cannot derive this complex wave function from any of the equations of the classical physics. For instance, the wave equation for a stretched string can be derived from Newton's laws. An electromagnetic wave equation can be derived from Maxwell's equation. But it's not the case of quantum mechanics complex wave function, which cannot be derived from anything. The essence of quantum mechanics lies in one particular equation known as the Schrödinger equation. M in this equation represents the mass of the particle and V is the potential energy of the system. This equation can in fact be derived in the case of free particles with zero or constant potential. But if potential energy is position and time dependent, then it is not possible to derive the Schrödinger equation. Even in that case, this Schrödinger equation is true and we take it as a postulate in quantum mechanics. Validity of this postulate is judged by comparing its implication with experimental observations. Now the biggest problem is that if you try to solve this equation, you would get a complex solution for psi of xt. There is no other way of getting a reasonable solution. Or in other words, no real wave function can ever satisfy the Schrödinger equation. This is a consequence of the fact that Schrödinger equation basically relates a first order time derivative to second order space derivative. This in turn is due to the fact that Schrödinger equation is based on the energy equation, which relates first power of total energy to second power of momentum. Now, what is the issue that we face since the wave function in quantum mechanics is complex? As you know, the complex wave functions represents two real functions simultaneously, its real part and its imaginary part. This means we cannot attempt to give a physical existence to wave function in the same sense of physical existence of, let's say, water wave, which has only one real value. So wave functions in quantum mechanics should be considered as conceptual devices. At the same time, it does not imply that the wave function have no physical significance. It actually contains all the informations which uncertainty principle allows us to know about the associated particle.